for the assignments, you can take down the questions. Macro shock result from high or low current passing arm to arm. This is first question. Second question, micro shock results from high or low current passing directly through the heart. Either high or low, that you have to tick. The third question is leakage current results primarily from inductive bar capacitive of AC power cords and electric transformers. That means you have to choose either inductive or capacitive or both. Next, leakage current can be reduced by adding a dash wire from equipment metal cases to a common dash terminal. That means it can be reduced between what are the two terminals. That's all. So these just 4 questions you can take it as assignments and then post. Thank you.
Yes, sir. So, good afternoon everyone present virtually here. So, we are going to have a continuation of bonding techniques. So, today we are planning to go with the SiOI, silicon on insulator, embedded channel, and the low pressure surface bonding, and the thermocompression bonding, and wedge wire bonding. These 4 topics we are going to see. We'll start from SOI embedded channel bonding. Right? See, the objective of this is to bond silicon dioxide with silicon. So we are going to have a 2 separate cross section where I am going to join silicon dioxide with the silicon. Before going with that, I want to draw the cross section of the micro channel. Let's say the micro channels are look like that. The substrate, it has its own micro channel. over the SiO2 layer, and over I call it as donor wafer or P-type Si wafer. So this is silicon dioxide. So this is my microfluidic channel. It has its own width, length as well as thickness. So this will probably carry some liquid. So you understand there are two portions. This is the substrate portion where it has micro channel. I can call it as A. This is the above portion, I call it as B, where I am going to embed silicon with the silicon dioxide. When I am going to encapsulating silicon with the silicon dioxide, I could form a micro channel on the system. So this is cross-sectional view. Cross-sectional view of micro channel. Let's start from the process, right? So initially it has a donor wafer. It is made up of a P-type semiconductor with the boron implanted, right? So along with that, we have a SiO2 layer, which is developed by oxidation process, either wet oxidation or dry oxidation. Anyway, it's a simple process. If we heat the silicon with air, if we heat silicon with air, silicon is heats up with 1000 degrees with air molecules, or I could call oxygen. We will form a silicon dioxide. So this is one way of formation of the silicon dioxide, right? So the donor substrate is there as a P-type, right? So what I'm going to do here, I'm going to, this is implanted P-type. Now I'm going to implant a active hydrogen on the surface of P region. That forms, we call it as implanted H2 ion region, right? So once I implanted for the P-type substrate with the H2 is hydrogen that forms a layer. So this is layer, I call it as implanted layer on silicon, P-type silicon. This is one way. I could call it as section B, right? I could call it as section B. But in the downstairs, I have a microfluidic channel. Using soft lithography, I could be able to, or either using a dry etching or wafer etching, or by a chemical etching, or by plasma etching, or even deep reactive ion etching. Either you can use any kind of etching. We could form, it is easy to form a channel on any kind of silicon substrate, right? Either I could use deep reactive ion etching or plasma etching or wet etching by chemicals. So either I could use any kind of etching, so I could form a good micro voids or micro channel on the substrate. Now my object is, I want to form a micro channel like this. I want to encapsulate or seal this channel, then only the flow of liquid is possible. Or I could say we can allow a predetermined volume of the gas or predetermined volume of the liquid can push through the channel for some measurement, right? So I want to form. What is next step? Next step, I'm going to embed these two. I'm going to embed these two into single layer. So after embedding, we could form like this. After embedding this, right, we form a micro channel like this. Silicon dioxide over the micro channel. This is silicon substrate, and over and above we have a implanted, right, implanted H2 ion. So we call it as, there are two implanted. One is implanted here, other one is called peak implanted. I call it as peak implanted implanted H2 ions, right? So peak implanted H2 ions. So what happened after this? After this, I'm going to apply some heat over this. The heat value around this is around 470-degree heat, because I have to remove the donor. This is the donor Si wafer. So I want to remove the donor Si wafer. So this is acceptor Si wafer, and above we have a H2 ion Si wafer. So I want to remove these two portions by applying heat, right? By applying huge heat value around 470 degrees Celsius, as well as I'm going to apply a energy, right? Hydrogen energy of 88 into 10 to the power of 16 centimeters square, right? The implant ion, acceptor implant ion at the rate energy of 40 kV. 40 kV energy I'm going to apply with the heat. So what happens? This heat along with the energy, huge energy, I could call it as a peak energy applied between this. So that will automatically remove or release the structure. Now the donor wafer is removed from the cross-sectional view. The donor wafer is moved away. Now the lower embedded portion of silicon with silicon dioxide was obtained. Now you could able to understand the microfluidic channel got sealed or encapsulated by the silicon dioxide. So this is the easiest method, the using SiO2 layer. So why I am calling SiO2 layer? Silicon on insulator. So silicon on insulator with the channel. The channel length probably it would be around 6 micrometer, and the cost length of maybe 100 micrometer, the thickness may be 2 micrometer of length, right? So with the length and as well as thickness of the micro channel, it will be given, right? This is called SiOI, silicon on insulator embedded channel. So this is one of the bonding techniques to bond silicon with the silicon dioxide, right? While bonding this, we have to follow the procedure of like this, right? So p-type is heat, p-type is energized with the H2 ions on the surface of the p-type, and as well as this is taken at this process taken at low temperature, right? Taken at low temperature. This process taken low temperature, but while releasing, right? This is, I could call it as bonding. So this call it as bonding, whereas while releasing, I'm using high temperature, right? High temperature, the value of 470 degrees Celsius, with the hydrogen energy of 8 into 10 to the power of 16 centimeter at energy level of electrical energy level of 40 kilovolt of energy attached. So this will automatically remove the donors with the acceptor. So this is acceptor. This silicon is acceptor which accepts silicon dioxide, whereas this is donor which donates silicon dioxide on the silicon. So finally we have a bonding of silicon and silicon dioxide which forms a nice microfluidic channel for any biomedical or any kind of applications, right? This is one. Next topic we are going to see here is low temperature surface bonding. Right? There are three stages. So we call it as low temperature surface bonding. Sir. So it has a three process. One is deposition, bonding, and release or laser lift off. What is deposition? So deposition, you could understand that silicon is deposited either by thermal evaporation or by this sputtering technique. We have deposited platinum on silicon on top of this. I could call it as a two section. Section A is silicon is coated with platinum, palladium, and the lower portion sulfur is coated with gallium nitrate and indium. So my object is to ensure I want to deposit palladium with indium. I want to bond. I want to make a bond of palladium with indium. So I could call the silicon and sulfur, we both can act as a supporting medium, right? So this is a mechanical support, silicon, palladium is supported by silicon, and the indium is supported by gallium arsenide, right? This is stage 1. So both can be taken in the CVD process or PVD process using either by using thermal evaporation technique or by sputtering technique. We have coated palladium and indium over the silicon as well as gallium nitride. The stage 2 is called bonding. It is happened only at 200 degrees Celsius. That's why we call it as a low temperature surface bonding. Here, I'm going to press both the section with a mechanical force of 3 megapascal on the surface of both the sides. So, the one side gallium arsenide carry indium and silicon carries palladium. Both can be pressed against to the face. So both the surface got heat trap, and because of the mechanical force and as well as we applying we are applying a mechanical energy temperature of almost 200 degrees Celsius with the mechanical force. What happened? The palladium and indium getting close together and contact together make a small ice melt between palladium and indium. So this is the stage 3. We call it as a laser lift-off process. I'm going to apply laser on bottom of this, right? I'm going to apply laser on bottom of this. So what happened? The application of the laser will remove silicon and sulfur. You understand one thing, the palladium and indium brought together and form a single layer, call it as palladium indium metal on the silicon. As well as you understand silicon and gallium nitrate got sandwiched by palladium indium. So this process I could call it as low pressure surface bonding, means surface bonding between two metals at low temperature. So it comprises of deposition, means deposition of PD and indium by PVD CVD process, and bonding is taken place with the help of mechanical energy with electrical energy about 30 minutes. So the bonding between palladium and indium happened and got together, right? It's just like a melted together and forms palladium indium process. After this, using laser component, I'm going to release the sulfur oxide, sulfur by removing, right, using mechanical force again, right, mechanical force. But very important that laser we have to use, so that will debond the gallium nitrate with sulfur, right? So this will debond it, right? And the third one we are going to see now called thermocompression wire bonding. The third one we are going to see thermocompression wire bonding. millisecond. So this is the third level called thermo-compression wire bonding. You understand we are applying heat by means of temperature, call it as thermo. Compression, we are applying force on not only heat along with the force, right? So this is a solid ball, solid wire bond. This is a solid wire bond, right, on the metal. So this finally got, right? Right? So you got the point? Thermocompression wire bonding. So it has a substrate and the substrate carries the metal patches on the substrate. So substrate could be the PCB, right? We are going to make a electrical connection with the help of thermocompression technique. So as I mentioned, what do you mean the thermocompression? We are applying necessary heat to melt or to bond, to make a bond of the metal A as well as the bond head metal, right? So this is carried by a metal wire capillary, and this as action of the wire can move down and up because we need a movement to make sure the metal connection, right? So this is called heating process. Why heating process? The heat is the perfect element of the mechanical phenomena which makes electrical bonding between these two patches. And the third one called pressing. Not only make the heat, we are going to press the ball, head ball, we call it as a metal head ball on the metal tap. So what happened along with the heat as well as force will make you some bonding between these two, right? After pressing, we are going to release this, right? I'm going to release, right? I'm going to release, sorry, I'm going to release. So this is wire. So I'm going to release like that. I'm going to release the capillary, right? So the capillary move upward. I released my wire and move upward, and sometimes it may extend it to next, right? So we made it one connection, which it may extend it to the next metal on the same substrate. Because it's a wire bonding, we may have a infinite number of wire bonding if it is necessary. So I can show you only one on the board. So the first one, thermo, second one called compression, and third one called releasing. So thermo compression wire bonding. So this is by means of temperature thermo, this is by means of mechanical force by compression, and the wire can be released by means of bonding. So thermo compression wire released called wire bonding, thermo compression wire bonding. Now we'll move on to the last one called wedge bonding. We'll see one by one. Wedge ultrasonic bonding. So here you understand this called wedge ultrasonic bonding, right? So this it has a substrate. It may be a PCB, it may be a PCB, right? It may be a silicon substrate, and it has a metal patches like this. So there is a metal patch. It could be a metal, either palladium, aluminum, or even a gold, AU, Al, or palladium, anything, right? So metal bond. So this is the tool which will apply a wire, right? This is the wire I'm going to use to make the bond. So the bonding is happened between this wire and this, and you understand the tool is moving from left to right, with the temperature of 100 to 150 degrees. So when I'm going to apply a temperature of 100 to 150 degree, I could call it as a low temperature. Why? Because we are using ultrasonic wave. We are using ultrasonic wave with the frequency of 20 to 60 hertz with the energy of ultrasonic wave. So the wave is always created a vibration as well as the local melting. So it happen between these two. So this vibration makes sure the reaction between these two metal and forms a metal bonding. As well as once this completed, the tool is removed, lifted up like this and moved to the next metal. So in that way, the metal bonding is taken care because of the ultrasound wave, right? So wave having its own mechanical vibration, that mechanical vibration creates the local bonding between metals of these two, right? So not only the mechanical vibration, it also having its own force of energy, mechanical force tool over there, right? So I could also show the 3D image of this, right? So once the bonding has been completed, right, it has moved from next one like this. So this is the last wire bonding technique. We call it as a wedge ultrasonic. So this is purely by means of the ultrasonic energy taken over the metal. So these two metals can be joined with the help of not only by the temperature, with the help of the fixed frequency range from 20 to 60 hertz of the ultrasonic. So today we can conclude that we have finished bonding techniques, right? So we started yesterday with the electrical bonding, and today we have completed almost the fourth technique we have discussed. Initially we start with the silicon on insulator, which forms a microchannel, and we understand how the microchannel is formed by employing silicon and silicon dioxide. So while forming silicon and silicon dioxide, we understand the boundary conditions as well, right? The next one we have come across low temperature surface bonding. So in there we are going to use, or we are going to bond two different metals like a palladium and indium with the help of a low temperature surface bonding with the help of hydrogen implantation technique, right? So that is also happened. So after making a contact between, after making a effective bonding between palladium and indium, we could easily remove with the help of laser. So there are two systems. One is donor substrate, other one is acceptor substrate. So the donor substrate will have some metal on that, we call it as a palladium. Acceptor have its own metal called as indium. So that can be happened in the low temperature surface bonding. The third one called as thermocompression wire bonding. You understand, because of the heat, I could call it as a temperature thermo. Because of the pressing, I call it as a compression, and because of the wire melting over the metal contact, I could call it as thermocompression wire bonding. The last one called wedge ultrasonic bonding. So this is not only by means of mechanical force, this has happened because of pure ultrasonic wave. So this will end up with the energy bonding of the thing. Tomorrow we will see what do you mean by encapsulations and what do you mean by sealing, right? There are I could call it as encapsulation is the technique where we could isolate the die. We could isolate our own die. Die is called as a complete electronic chip which could isolate it from the other circuit by making either plastic mold or non-conductive mold, non-conductive molding, right? It's called encapsulation. Then the second word called sealing. Sealing will also like encapsulation, but this will make a tight or airtight bond of or airtight sealing will happen over just like a microwave, just like a SiO layer on the microchannel. What is microchannel? The microchannel is properly embedded with the two different material and forms a voids inside the channel. Like sealing is also covers lot of cavities and air gaps or fluid gap or even gas gap. What means? So what is the objective of the sealing? The objective of the sealing is very important to seal or to tightly bond the two different material and forms very tightly environment like a airtight sealing. Whereas encapsulations are the technique where we could form a molding material on the die that forms the encapsulation. I'll draw a small diagram about these two. What is encapsulation? Let us consider this is my die, right? This is my die called as a chip. So it has its own electrical connections, right? It has its own electrical connection on the substrate, right? What do you mean by encapsulation? Encapsulation is completely molded with some special material. I could call it as an insulator, right? It could be a plastic. So it won't affect any electrical parameter or bonding, but I could understand my die is properly sealed with some molded form. Call it as encapsulation. What is sealing? Sealing is little different. So sealing is, you understand, there is a there is a there is a channel and that can be tightly bonded with some silicon dioxide. This is silicon dioxide and silicon. So this is my channel. So I want to create a tight sealing, which means I should protect this void, or I could say this channel will allow some special liquid or gas flow in a microliter, nanoliter. So I should worry about sealing because sealing will ensure the bonding between silicon and silicon dioxide, whereas encapsulation, this is encapsulation. So this is encapsulation. So encapsulation, which is a molded form over a IC. So my IC is protected from the environment. So encapsulation is the objective of the encapsulation. I should isolate my electrical chip from the environment. Whereas sealing, this is sealing.